Rotational motion of a particle. Rotational motion of a particle deal with motion of a particle under the influence of central field of force. For example, the motion of an electron around the nucleus of an atom. For a single particle executing such a motion, the Schrödinger equation can be solved exactly. In this case, first we deal with the rotational motion of a particle in a plane, that is, the particle in a ring. Particle in a ring. In this case, we are dealing with the Schrödinger equation and the wave functions. Consider a particle of mass m rotating in a circle of radius r in the xy plane. If the potential energy of the particle is 0, potential energy is represented as V. The Hamiltonian in the simplest form can be represented as H operator is equal to minus h square by 8 pi square m into dou square by dou s square plus dou square by dou y square. In this case, the motion is circular, so it will be more convenient to express h operator in terms of polar coordinates, that is r and phi. The Cartesian coordinates x and y are related to polar coordinates as x equal to r cos phi and y equal to r sin phi, where phi is the angular variable which varies from 0 to 2 pi and the radius r is a constant. Hence, equation 1 in polar coordinates can be represented as h operator is equal to minus h square by 8 pi square mr square into dou square by dou phi square, that is equal to minus h square by 8 pi square I dou square by dou phi square, where I equal to mr square. The eigenfunction f of phi, or simply it can be represented as f, that will be a function of phi only. So the Schrödinger equation can be represented as minus h square by 8 pi square I into d square f by d phi square is equal to ef. That is equation number 4. That can again be represented as d square f by d phi square plus m square f equal to 0, where the value of m square is equal to 8 pi square IE by h square. That is equation number 6. The solution of equation 5 can be represented as f equal to n sin m phi, f dash equal to n dash cos m phi as the real set, and f2 dash is equal to a into exponential plus or minus im phi as the imaginary set. The trigonometric forms 7 are also called circular harmonics. Equations 7 and 8 are equivalent in view of the theorem exponential plus or minus im phi is equal to cos m phi plus or minus I sin m phi. That is given equation number 9. In Schrödinger time-independent equation, you have studied that Schrödinger equation is a second-order differential equation. It has several solutions. Some of them are imaginary and have no significance. The only acceptable solutions are those that satisfy the continuity and boundary condition. Continuity and boundary condition states that the wave function must be continuous, finite, and it is single valued too. In this case, the functions 7 and 8 are finite and continuous for all values of phi and m. They are single valued too, since the angles phi and phi plus 2 pi represent the same point, and the property of single valuedness demands that f of phi is equal to f of phi plus 2 pi. Using the real set equation 7, we get sin m phi equal to sin m phi plus 2 pi, cos m phi equal to cos m phi plus 2 pi. This is possible only if the value of m is equal to 0, plus or minus 1, plus or minus 2, etc. Similarly, a exponential im phi is equal to a exponential im into phi plus 2 pi. That is equal to a exponential im phi into exponential I into 2 pi m. Exponential I into 2 pi m is equal to 1, or cos 2 pi m plus I sin 2 pi m equal to 1. Normalization and orthogonality. The normalization factor n can be determined as follows. Integral 0 to 2 pi n sin m phi square d phi equal to 1, or n square integral 0 to 2 pi sin square m phi d phi is equal to n square 0 to 2 pi 1 minus cos 2 m phi by 2 into d phi equal to 1. Sin square theta is equal to half into 1 minus cos 2 theta, or n square into pi is equal to 1, then n is equal to 1 by square root of pi. Similarly, n dash is equal to 1 by square root of pi. The normalized real set of wave functions are f is equal to 1 by square root of pi sin m phi, and f dash is equal to 1 by square root of pi into cos m phi. For m is equal to 0, then the value of f dash is equal to 1 by square root of pi. For the imaginary set, integral 0 to 2 pi a star exponential plus or minus im phi into a exponential plus or minus im phi into d phi equal to 1, or integral 0 to 2 pi a square d phi equal to 1. A square is equal to 1 by 2 pi and a is equal to 1 by square root of 2 pi. Hence, f2 dash is equal to 1 by square root of 2 pi exponential plus or minus im phi. When the value of m is equal to 0, f2 dash is equal to 1 by square root of 2 pi. The functions 1 and 3 are orthogonal when it satisfies the condition 1 by pi integral 0 to 2 pi sin phi cos phi d phi equal to 0.